It's almost tea time, so let's continue with our last talk for the day by Professor Michael Shearer from North Carolina State on the Kawahara equation, a fifth-order dispersive PDE.
Okay, thanks. And thanks to the organizers of the workshop and the organizers of the program, I guess. That includes myself, of course. So, yeah, so I changed the title slightly. And let's see, let's see, is this working? Oh, pressing the wrong thing. No, it's okay, I got it. Yeah, there we go. Yep, thanks. Yeah, so special thanks to Mark, Patrick, who was a student with Mark Hoffer and my postdoc at NC State, and to Tom Bridges, who supplied some neat ideas about dynamical systems. Okay. I'm not able to go forward. Once here. Okay, and that should work. I'll go back. Okay, good. Yeah, so I had earlier at lunch, I had a request to explain what nonlinear means, hence this slide. And so things that you're all familiar with, I'm sure, but a couple of points maybe. So the inviscid Burger's equation we're familiar with. The solutions are constant on characteristics as a method for solving the equation initial value problem with smooth data. The Riemann problem is of particular interest, so an initial jump from a left state to a right state. And the solution is very simple. So the weak solution is either a lax shock if the left state is larger than the right, and a rarefaction wave if the left state is less than the right. Burger's equation smooths out that story. So there are various remarks here. This is a nonlinear heat equation with a viscosity mu, which has to be positive, of course. There's the Cole-Hopf transformation, which allows you to solve Burger's equation, initial value problems using the heat equation. There's energy decay, and there are smooth solutions. So all of these things are different from the inviscid Burger's equation, which is a hyperbolic conservation law. The KdV equation, so now we're explaining higher order PDEs, not only nonlinearity, and nonlinearity, of course, was the quadratic term. The KdV equation, if we add dispersion to the Hopf equation, we also get a shock wave, but a dispersive shock wave, which I'll show you has oscillations instead of a jump. And if the left state is less than the right state, you get a rarefaction wave, but with small oscillations. Okay, so the Kawahara equation is even higher order. And when alpha is equal to 0, this is known as KdV5. But the sign of alpha when it's non-zero actually is significant, which I'll show you. The solutions are much more complex, and I'll show you a Sprenger-Hoffer picture here, computations on the left and the right are the same initial data. So this is a Riemann problem jumping from 1 to 0. And you see that something that looks like a constant, but actually I'll show you that in fact it's a solitary wave or half a solitary wave. You see something that is here, looks like a periodic wave, and then something which looks like a DSW, dispersive shock wave, called as a traveling dispersive shock wave, because everything moves to the right. Okay, and here's the famous dispersive shock wave with the constructions either using Riemann invariants for the KdV equation or L's method if we don't have that facility. And L's method depends on identifying parameters, wave number and amplitude of harmonic waves, wave number going to 0 for a solitary wave at the leading edge, and an amplitude that's related to the speed. So there's a speed in front and there's a speed at the back, which is just the phase velocity of the harmonic waves. All right, so in the middle, there's a modulated periodic wave, and this is the envelope here is actually a rarefaction wave solution for the Whitham modulation equations. Okay, all right, so I had another request. The other request was to include some history, and I had even less time to do this. So here's a little background on the Kawahara equation and a small number of studies of the equation. So the formulation was due to Kawahara, actually, I think based on what earlier work of Kuramoto on water waves. And that was back in 1972. There was also a connection to shallow water waves by Hunter and Scholl, and they pointed out, as had Kawahara, that if you have a balance between gravity and surface tension effects, then you get both third order and fifth order dispersion. KdV5 with alpha equals 0, Sprenger and Hoffer studied traveling waves via modulation and also using shock jump conditions. And that's very relevant for what I'm going to talk about. Spectral stability, all sorts of spectral stability were studied by a variety of people more recently than the 1980s and 90s. So spectral stability, stability of periodic traveling waves, and then stability and instability in the context of the Kawahara equation. I'm going to rely on theoretical work of Toland, Buffoni, Champneys, and to some extent others, characterizing periodic waves, solitary waves, with analysis, but also numerical simulations. The trouble with the Kawahara equation is that it's fiendishly difficult to get hold of explicit solutions. All right, so here, let's return to the equation, and here are some basic facts. So first of all, if I scale x, t, and u, we can reduce alpha to 0 plus or minus 1 without loss of generality. So that's kind of handy. So there are just 3 cases to be considered. And we'll look at the dispersion relation. So to remind you, we look for exponential solutions with wave number k and frequency, temporal frequency omega. So they're traveling waves with speed omega over k, the phase velocity. And if we linearize about a background state u bar indicating some sort of average if we're dealing with periodic solutions, a background state u bar, then here's a linearized equation, here's the dispersion relation, substituting powers of k wherever you see a d by dx and omega or minus omega for d by dt. So the phase velocity is quartic, and the group velocity is also quartic, but with different coefficients. And here's where alpha comes in. When alpha is equal to 0, let's start with the simplest case, we have a quartic contact with k equals 0 at u bar. Okay. The alpha equals minus 1 case is similar, but it's quadratic contact. But the most significant difference between these 3 graphs is that for alpha equals plus 1, the dispersion relation and the phase velocity and group velocity are both non-monotone. Okay. And in fact, they're non-convex as well, right? They're convex for high values of k, but and convex for small values, but there's a change in convexity. Okay, so it turns out that for what we're going to study, these differences don't make any difference. All right, so there are just subtle differences between alpha equals plus 1 and minus 1. So we're going to look at traveling waves. So with a speed c, substitute into the, let's say, KdV equation to start with, and you integrate once and you get a second order equation for various values of a and c, you get different phase portraits. Very easy to study. There's a Hamiltonian. You can write down explicit solutions, periodic conoidal waves, and they're embedded in the phase diagram in a solitary wave represented by a homoclinic orbit. Okay, and there are explicit formulas. The Kawahara equation has a similar ODE equation for traveling waves. Again, we have the wave speed and a constant of integration, but it's a 4th order equation. So the phase portrait is in 4 dimensions. However, as we'll see on the next slide, we also have a Hamiltonian. All right, so first of all, we're going to use the Galilean transformation. This equation is invariant under increasing the base state of a wave by, say, UB, and then it just goes faster with given by that speed, that base state UB. All right, so the thing that Patrick did very effectively was to compute a library of periodic traveling wave solutions, and we also looked at Stokes expansion. So I'm going to show you a little bit about those 2 aspects. The work of Buffoni, Champneys, and Toland, and to some extent others, they looked at the existence of periodic and homoclinic orbits for a related fourth order PDE, but P is a real parameter. It's not just alpha equals 0 plus or minus 1. But you can relate this ODE to the traveling wave ODE pretty simply. The 0 on the right-hand side actually turns out to be significant and will accommodate any value A. All right, actually, I'm very dry. Excuse me a second. So, yeah, read among yourselves, and I'll come back to you. So here's the equation again. We'll introduce the wave number by rescaling the independent variable that introduces a k for every derivative. So now we have three parameters, a, k, and c, which we can change. Alpha we're regarding as just having three cases. So that's pretty straightforward. Okay, so three parameters which are very natural for the ODE, but we're going to relate them to three crucial properties of a periodic solution. So we're going to have the mean over a period. Phi, by the way, here is 2 pi periodic. The amplitude, which we'll define as just the difference between the maximum and minimum, and the wave number k. We have a Stokes expansion in those terms. So depending on u bar a and k, we get an expansion. Actually, we will use the order a squared terms, both in the speed and in the variable phi. But the formula itself is not important. It depends on not only on a squared, but on k. All right, so yeah, so the Hamiltonian, of course, the PDE is Hamiltonian, but we're not going to use the PDE Hamiltonian just for the ordinary differential equation. So here's the first integral multiplied by u prime and integrate once. I'll keep a because a is a constant of the flow anyway. And then we can write the Hamiltonian in the usual way, where we get a first order Hamiltonian system. This is not a standard choice of terminology, but you can see that it's Hamiltonian. So again, it's a system a first order system in 4 dimensions. But the traveling waves are confined to level sets of the Hamiltonian. Hamiltonian is constant, as it always is for a Hamiltonian system, on the flow. And so we can parameterize those 3-dimensional level sets by 3 of these 4 variables, right? U prime, U double prime, U triple prime. Gets a little bit mixed up in P, but that's fine. Okay, so if I choose U double prime, and U prime, then I can solve H equal to a constant for U triple prime. Okay, so we can look at the dynamics just in 3 dimensions, and we're going to do a fair amount of that. All right, scaling properties. I told you about Galilean invariance for the PDE. Here's how it shows up for the ODE, for the traveling wave. If you add a constant to the traveling wave, it just moves faster. Okay, a positive constant, I guess. So yeah, so let's see. I think I probably mixed up the notation here. So U satisfies the ODE, then we can change the constant A by changing the speed C, and here's how that works. Okay, so it allows us to set A equal to 0, and then we can recover the solutions for different values of A by changing the speed and changing the solution. Okay. All right, so we can compute periodic solutions on a reduced parameter set. So we can set the mean 0 because of property 1, or we can set the constant of integration equal to 0. Okay, so we can just think of one parameter family of solutions. All right, existence results are found in the various papers of Buffoni, Champneys, and Tolland. I keep repeating this reference, partly because they're terrific papers, very theoretical actually, but also because Tolland was a very good friend of mine when I was a postdoc. Okay, now let me just say a little bit about the numerical method. Now this, Patrick's not in the audience, but maybe he's online, I'm not sure. But this is my version of what he described to me about the pseudo-spectral method or spectral method, which I like to just call a Fourier series method. So we're going to look for solutions in the form of a truncated Fourier series. So I've included the wave number here, And so this is the cake C, which would make, where we introduced a change of variables to get a 2 pi periodic solution. But here we'll keep the wave number. We substitute into this equation, and I've set the constant of integration to be 0. We're going to choose C, and we get an equation like this. So all the linear terms just give me a polynomial in K, with coefficients, of course, depending on which mode we're looking at. And then we've got a nonlinear term, which just involves squaring this expansion. If we project this system of equations, so we get an equation for each capital N, we get an equation for the variables un hat, but also the wave speed C. We project onto each of the modes, then we get the right number of equations for the right number of variables. And then for u bar equal to 0. So here's the beginning strategy, and this is something that Pat and I talked about endlessly, and I think I've got it straight. If u bar is equal to 0, remember we're allowed to do that by Galilean invariance, and we choose k, then we've chosen two variables, and now we want to find the speed and all of these UNs. Okay, so let's let C be given by the Stokes expansion up to order a squared. So it's an explicit formula, and we know what the corresponding U2 will be if we take n equals 2 in the truncated expansion. All right, so this is not an exact solution, so we know we have to have additional terms. So, but anyway, we'll look at that as a starting estimate for the speed and the solution for fsolve, for the MATLAB solver. You've got a set of simultaneous equations. fsolve is set up to do that. Now you increase capital N depending on k, and you keep going until the difference between successive UNs in some norm, presumably the L2 norm, some of the squares of the coefficients, is below 10 to the minus 12. That's, perfectly arbitrary tolerance. And then having done that, you've got UN for this particular choice of wave speed. We haven't changed the wave speed. We just calculated UN. Okay, and so now we can calculate the amplitude and the average of that UN for the Stokes expansion wave speed. Okay, so we got one solution. All right, now we vary the speed with small increments, go through the same procedure, but now our initial estimate is the previous UN. Okay, and then you get a new UN, you can calculate the amplitude and average of that new UN. So now we've got K, amplitude, and the average U bar for these truncated Fourier series. Okay, and I think it's simple, but it's clever. All right, so we get a library of these traveling waves, periodic traveling waves with speed given by those three parameters. Now, I mean, I should be honest and say that, of course, we have fixed C at each stage. So really, this is implicit in terms of C, this dependence on U bar A and K. So there's a little inversion of the formula. Okay, now I'm going to switch topics. And yeah, this always makes me so. This is something else that I learned about, but it's very basic if you take dynamical systems. So we're going to look at the flow map, psi of C, and write the fourth order equation as a first order system. The flow map is just the solution of the linearized problem, but in matrix form. So we linearize about a periodic solution, which I should have said somewhere, there's U of C. And when I linearize, I get, so here's the linearization, the coefficient, it does depend on C. Okay, so then I set an initial condition, this matrix will be the identity in 4 dimensions, and then we can integrate. Okay, but we integrate over one period. Okay, so the period will be, yeah, we're looking at the full equation, so period 2 pi over k. Okay, I've got a little piece of art on the next slide, I'll warn you. Oops, okay. Yeah, so if we have a periodic orbit, capital U of C, and here it is actually as little U of C in blue, then we've got this flow map evaluated at t equal to the period, 2 pi over k. So that is a matrix called the monodromy matrix, or in some countries, the monodromy matrix. Okay, so then we look at eigenvalues and eigenvectors of that monodromy matrix. We know because of the Hamiltonian structure that lambda equal 1 is a double eigenvalue. It actually has algebraic multiplicity too. The remaining 2 eigenvalues are reciprocals of each other. And the other property is that not only are they reciprocals of each other, but if they're complex, then they sit on the unit circle. Okay, so here's a picture of how the monodromy matrix works. You choose a V, you integrate for one period, and you end up somewhere. And if you end up at a multiple of V, then you've got an eigenvalue and an eigenvector. And this is all in 4 dimensions, remember. Okay, so when lambda is bigger than 1, this is just an example, we'll look at different cases. When an eigenvalue is bigger than 1, then we get a 2-dimensional unstable manifold. It's in R4, but remember all the solutions, so the unstable manifold is a nonlinear object that's related to this linear argument. We get an unstable manifold, but it has to lie on a level set of the Hamiltonian. Okay, so it's 2-dimensional, but it lies in a 3-dimensional submanifold of R4. Okay, so the Floquet multipliers, they're kind of interesting. So I like to call this the dance of the Floquet multipliers. There's no music, I'm afraid, but you know. And the point is that as we change the periodic solution, we change the Floquet multipliers, and I've done these sort of in sequence. So here are the 2 at lambda equals 1. This is the unit circle, of course. And then there are 2 others. One is bigger than 1, and the other one is 1 over that value. Here they are coalescing at 1, so all 4. Here they are splitting off into the complex plane on the unit circle. So they're doing a little journey around to -1. Here they are at -1, and then they split off, and then they go back, right? They're just sort of dancing along like this. I do a forward roll for the unit circle, but it wouldn't be pretty. Okay, so there are various ways to think about this. And one is to look at the location of Floquet multipliers as we vary these parameters. So here's how we do it. So we'll look at A against K. So each A and K represents a periodic solution with mean 0, 2-parameter family. The plus means that we've got positive real Floquet multipliers. Minus means we've got negative ones, right? And there are always 2 of them at 1, which we're going to ignore. Now, when alpha is equal to +1, this picture actually has, I mean, you can see it's sort of a dashed blue-red curve, and it actually contains more information, which is shown up when alpha is +1. So red is where lambda is equal to 1, these 2 extra Floquet multipliers, non-trivial ones. And blue dash is where they get to -1. So in between, they've danced around the unit circle, right? There's complex conjugates. Well, for you, I guess it's this way. All right. And so the shaded part is where the lambdas are complex. And of course, there's a very narrow region in each of these dash dot curves. They're very curious. And then I asked Pat about this gray rectangle, and he said, well, no, actually, I'm lying. He didn't say, I'm making it up. It's a state secret, what goes on behind the gray rectangle. Okay, so notice that we're getting down to small amplitudes and comparatively small values of K, and the wonderful numerical method I explained doesn't work in that gray rectangle. Okay, so now here's another way of looking at these Floquet multipliers and what's going on. So if I can evaluate the Hamiltonian as a function only of the wave number by fixing the constant of integration and the wave speed. Now I've switched back to that other triple of parameters, okay? But this is also convenient. So now I can graph H as a function of K. I've forgotten what alpha is in this picture, but in any case, so it doesn't actually matter. the point is that whatever the value of alpha, you get a non-monotonic H, and it has lots and lots of extrema. And we've had to blow up this graph in order to see them. You notice the scale here is 10 to the minus 5. Okay, so let's look at that maximum and see what's going on with the Floquet multipliers. So I'm going to look at the graph of H, take a place where I know that the lambdas have to be 1. That's at an extremum. So all of the lambdas are equal to 1 at actually the maximum. And when I plot the real part of the Floquet multipliers as I change H, or change K, if you like, first of all, I get, as I drop from the maximum, I get 2 values of K, K1 and K2, with the same value of the Hamiltonian. And so they each have 2 non-trivial Floquet multipliers. When the real parts are the same, that means they must be complex Floquet multipliers. And when the real parts are different, of course, then the Floquet multipliers are real. So that's the way to see this. When you drop down from a maximum, you get one side with real Floquet multipliers, for which we understand stable and unstable manifolds. And the other side, we get complex, where we know very little, except there's a bifurcation to a torus. Okay, and then if I move even further down in this picture, so these dots will move to the left, this dot will move and encounter another bifurcation. And then we get all real eigenvalues. And then we know that both periodic solutions have stable and unstable manifolds. Okay. Yeah. So we've got the same speed and the same amplitude, same constant of integration, but different Ks. And of course, as we change the Ks in this picture, we get different values of the Hamiltonian. But these 2 periodic solutions have the same Hamiltonian. Okay, so now we're going to look at really the topic in the title, which I didn't refer to, but now will. And that is that we have an unusual set of traveling waves. And the traveling waves, which were already identified for KdV5 by Springer and Markhofer, are between periodic orbits. And also between constants and periodic orbits. All right, so we'll look at a solution, a traveling wave solution. I'll make it smooth. I mean, it's naturally smooth. And we'll assume that it converges at plus or minus infinity to a periodic traveling wave, where the U's have their own parameters, U, A, and K. All right, so these are periodic traveling waves. We're going to look at the ODEs and average everything in sight. Okay, so the average of a quantity that depends on the periodic wave is just the average over that period. So here it is, keeping the K. So the ODE, all that has linear terms for the derivatives, so all those terms drop out, and we just get this algebraic equation. And then for the Hamiltonian, after some integration by parts, and rearranging, we get this expression for the Hamiltonian. Okay. Now the point is, my point here is that A and H have to be constant on this traveling wave, right? The constant of integration and the Hamiltonian. So these 2 values have to be the same, and these 2 values have to be the same. I just write down that as jump conditions. Okay. Now, buried in here is a speed. Okay, so that should be part of the solution. But all of these averages can be calculated from the spectral method. We've computed these periodic solutions. We can compute all the terms in these equations. But the one thing we don't have is that the speed, which we said was a function of the average amplitude and wave number, has to be the same for both the periodic waves. So there's a third jump condition. Now, these are very similar to the conditions that you would derive from the Whitham modulation theory. And indeed, that's what Springer and Hofer did. But to me, what's odd about that is that we're looking at traveling waves. Whitham modulation equations are PDEs. Why do you go back to PDEs to understand something about traveling waves? So I'll come to why the Whitham modulation equations are important. But for the time being, I've got this rather elementary derivation of jump conditions. But notice that these are just necessary conditions. If we have a traveling wave that has these limits, then the limits must satisfy these jump conditions. All right, so first of all, we have to solve the jump conditions. And I'm going to do this in a rather abstract way, but it has something of interest. So it's 3 equations, but there are 6 unknowns. Now, we're going to use bifurcation theory. So first of all, let's just agree to set the average of the periodic solution on the right to be 0, and we'll fix an amplitude on the right. Okay, that reduces to 4 variables, 3 equations in 4 variables. So if we're going to use bifurcation theory, we better have a trivial solution. So a trivial solution, obviously, is that the 2 periodic solutions are the same, right? The A pluses are the same, the U bars are the same, and the Ks are the same. Okay, so here we go. The trivial solution should be U bar equals 0, A minus equals A. But then what do we do with K plus and K minus? Well, if they're going to be equal, we may as well let this mu be 0. And so we're changing variables from K plus minus to new variables mu and a bifurcation parameter K. So at the trivial solution, this K plus and K minus are equal, and this is why I made it a half the average, because then I can call it K. So we're looking for wave numbers which we get bifurcation in these equations. Now, so we look for, how do you find bifurcation points? You take the Jacobian matrix, find out where it's singular. It only depends on K at this point, because we fixed A and we fixed U bar, right, on the trivial solution. So now we'll get places where this is singular, and we get curves that depend on A, curves in the Ka plane. And then we need to find non-trivial branches. I'll argue that they should be transcritical, but we're going to parameterize them not by the bifurcation parameter, but by U minus bar, because that's what Springer and Hoffer did. All right, so for a fixed A, K is a function of A, and J is labels a sequence of such points. And then we get A minus and K plus minus as functions of U minus bar, with U minus bar equals 0, right, the starting point. We're at the trivial solution when U minus bar is 0. Okay, so this is just a schematic of what bifurcation curves will look like. So here are the bifurcation points, values of K for which the Jacobian is singular. But in fact, there are lots of these points. Okay. And what's the significance of these curves? Well, if I've got a point away from the green dot, then that has variables, that has coordinates, not only K plus K minus, but K plus minus K minus, and A. And I can parameterize it with U minus bar. So each point on the curve represents 2 periodic solutions that satisfy the jump conditions. All right, and here is what that looks like. First of all, these bifurcation points lie on curves depending on A. So here's K as a function of A. There's another, so I might call this K1 of A, K2 of A, K3 of A, and so on. Every point on each of these black curves is a bifurcation point. It's very unusual for bifurcation theory. So just to show you what this looks like, we've chosen 3 bifurcation points, B, C, and D, chosen for convenience of representing the results. And here we plot the amplitude and the 2 wave numbers. The amplitude on the left, the amplitude on the right is A, fixed by this value. So let me just talk you through these curves a little bit, because they're a bit hard to read when if you've not seen them before. So first of all, we're parameterizing the curves with U minus bar. Red is K plus, the wave number on the right, and blue is K minus, the wave number on the left. So at U minus bar equals 0, they're equal. That's the trivial solution. Okay, and what's the value of A? It should be at the green dot. Okay, so let's look at B. What's the value of A? It's about 3. No, sorry. Is that right? Did I get them mixed up? Should be about 2.6. Yeah, and maybe I've got bad perspective here. Yeah, it's between 2 and 3. Good. At C, the value of A is about 3. And again, the K's are equal, and the K's for B should be about 0.5 something. So yeah, but just below 0.6. So each of these pictures is a curve of combinations of two periodic solutions that emanate from these 3 points. And in fact, we've got lots and lots and lots of them, right? It'd be interesting to prove, or try and prove, whether there are actually an infinite number of these black curves, bifurcation curves. Okay. All right, now I've talked about the necessary conditions, that's the jump conditions. Now we want to know, where do the traveling waves come from that join periodic solutions? So for that, we have some magic from Patrick to draw these pictures. So we suppose U plus and minus are periodic and satisfy the jump conditions. So, but with real Floquet multipliers. We compute a stable manifold for U plus. So the periodic solution is in black. The stable manifold, because the Floquet multipliers are in this case, between 0 and 1, is just a cylinder, or is, if you like, it's topologically or diffeomorphically a cylinder. However, if you're near lambda equals -1, remember you have to go around twice. I didn't explain that, but in the flow map, when you have your vector v, which is an eigenvector, when you go around one period, all that happens is you flip, right, and then change the length of v. So you have to go around twice to recover the eigenvector. All right, and that results in in this case, the unstable manifold being diffeomorphic to a Möbius strip, right? So it's a little hard to see, but if you start on one side of the periodic solution, and you can convince yourself that you have to end up on the other side. Yeah, it's not completely unambiguous. Okay, so where do the traveling waves come from? So here we use the fact that the Hamiltonian dynamics can be represented in 3 dimensions. So in each of these figures with U prime, and U double prime, I'm showing various shapes and so on. But for each value of U prime, U double prime, there's also a value of U triple prime, which contributes to the Hamiltonian. I don't care what their value is. It can be calculated from the constant Hamiltonian. Okay, so now I've got a periodic solution in blue dots, and its unstable manifold as a blue shaded area. And the orange is similarly the stable manifold of the periodic solution with orange dots. And they intersect. We're going to stop them at U equals 0. Okay, so you can't really see this very clearly. But, oh, I might have lied because U equals 0 doesn't show up here. Maybe it's U equals, it's some constant value of U that was convenient. And then we'll blow up this little place where it looks as though they intersect. And we're still in U prime, U double prime. Here are the 2-dimensional stable and unstable manifolds. And they fit together perfectly in 3 dimensions and transversely. But they're also lying on the Hamiltonian, a level set of the Hamiltonian. So let's visualize it that way. We'll fix U, so we get a Poincaré section. The level set of the Hamiltonian is 3-dimensional, but in the Poincaré section, it's 2-dimensional. And indeed, both of these curves have to lie in that Hamiltonian, that level set. And here they are crossing transversely. All right, so why is this useful? Well, the crossing point tells me a starting point for the ODE. Start at that crossing point, integrate with C decreasing, you get a blue oscillatory wave, not exactly periodic. Integrate with C increasing from 0, you get an orange wave, and they converge to periodic solutions. It's a little bit of a cheat because it's a very unstable process. And Patrick has other magical ways of computing the traveling waves, having got an approximation from this construction. Okay, now, all right. Yes, a little louder, I can't quite hear. is it, what was I? It's a traveling wave. So these are ODE solutions. So if I start near the blue curve, right? So any point near the blue curve in the direction of the eigenvector of the whatever it is, the flow map, then I integrate. So let's start up here. So I start, say, on the edge of this blue surface. I integrate round until I hit u equals whatever it was. I think it's 0.5. And then I stop. I do it again for a smaller perturbation, and I get another curve. That's how these surfaces are constructed. Now, they're really in 4 dimensions, but we know that the level set of the Hamiltonian has that 4th variable that depends on the other 3. So these 2-dimensional surfaces show up in the Hamiltonian, but although the Hamiltonian is 3-dimensional, if I freeze u, which I'm doing on the blue curves, and the blue and orange curves, then it becomes 2-dimensional, okay? Because I'm just solving for u prime, u double prime, and u triple prime in an equation in which h is a function of u prime, u double prime, u triple prime, and u, which we're fixing. Okay, so this is a 2-dimensional gray surface, and these curves were constructed with a constant value of u. So in that Poincaré section, we see just 2 lines crossing in an essentially flat surface. Okay? And from that, we can reconstruct the traveling wave joining 2 periodic solutions. All right, now there's another little wrinkle to this story, and here it is. So we can connect a solitary wave to a periodic wave. If I look at this picture when alpha is equal to -1, it looks as though we're just connecting to a constant. And here's the periodic wave. And it's a little clearer in alpha equals +1 that actually we're connecting to something else. It's got a bump here. Okay, so what we did was we used, let's see, so the fact that if I look at the base state of a solitary wave, look at u minus equals constant, then we have a stable, we have a 2-dimensional stable manifold and a 2-dimensional unstable manifold. Because we're looking on the left, we're only interested in the unstable manifold. And you trace out the unstable manifold and find that it follows the solitary wave. And the reason for that is that the stable and unstable manifolds of a constant intersect to give you the solitary wave. So if you go out on the unstable manifold of the constant, you have to follow the solitary wave. Okay, and that's what's happening here. The solitary wave, right, there's a little bump here, and that's that little loop here. And then, sorry, that's not the little lump. Yeah, the big dip is the big dotted portion, and the little dotted portion is this local maximum in the solitary wave. So this is an oscillatory solitary wave for alpha equals +1, but actually, when alpha is -1, the same construction works, and this is also oscillatory. It's just on a much smaller scale. You get oscillatory solitary waves, and the reason is that the eigenvalues of u minus are actually complex. So the unstable and stable manifolds actually spiral around themselves. They're like, you know, some sort of ice cream cone, which is all rolled up, and when they intersect, then you get these oscillatory solitary waves. All right, so here you see it connecting to a constant and then a maximum, and then trying to follow the dashed line, which is actually the solitary wave. But instead, because you're on the unstable manifold, you connect to the periodic solution. And similarly in figure D. All right, so this is a description of how that works, which I think, you know, I've already said in outline anyway. So let me skip. So then I want to make a few remarks about modulation theory and how the analysis is almost the same as what we've done. Here's the Kawahara equation written in conservation form, and here's the Hamiltonian version. So it's another first integral of the Kawahara equation, also written in conservation form. So we can use modulation theory for periodic solutions of of these equations, and so we we just average, but we have to introduce these additional variables, the slow and fast variables in space and time. So here I've explained, so the scale phase variable, depending on capital X and capital T, which are just scalings of space and time with a small parameter epsilon. You look for an expansion which has the periodic solution as the leading term, a small parameter in front of another 2 pi periodic solution, depending on capital X and T, but U bar and A and K are all functions of X and capital X and T. All right, so we average over a period, and we get a leading order. And by the way, leading order means epsilon is equal to 0. So let's not bother with this term. Okay, we'll just average over a periodic solution, but regarding A, K, and U bar as variables. So here are the equations written in those slow variables, capital X and capital T. And these are fast variables. I could always get confused between slow and fast. And so here's what looks like the average of the ODE, but it's actually of the PDE. And similarly, this looks like the average of the Hamiltonian, but it's actually the average of the second conservation law. Okay, but we got X and T, so it's a system of conservation laws, the modulation equations, with conservation of waves, which is, so K and omega are functions of capital X and T. So here's the third equation, and we could look at jump conditions for these equations. Okay, but the point is, so here are the jump conditions. The point is that this last equation for a traveling wave is trivial, because the traveling wave speed has to be the same as the periodic wave speeds, right? They're all traveling waves. And if you do that, the speed is omega over K on each side. This is trivially satisfied. So the equality of the speeds is crucial in these to understand these jump conditions. Okay, so the other thing that's interesting is that maybe the traveling waves with periodic solutions with the same speed are not the only solutions, right? And so I want to show you, or maybe I did show you already. Yeah, I did show you already that there are, this was right at the beginning, there can be other solutions of Riemann problems which are not just traveling waves. Here was this picture from Springer-Hoffer 2020, where you've got a lot of structure here. You've got there's the solitary wave, what I would claim is a solitary wave, as a trailing edge and connecting to a periodic wave. Here, it's obviously not periodic, but it is nearly periodic. And then a traveling DSW. All right, and then I had a final summary page. Okay, so I did want to point out there are several unresolved issues. How do we deal with non-real Floquet multipliers? And how do we deal with PDE solutions that join periodic solutions, but they could be periodic solutions that are moving apart? Well, what's happening in between, or moving together, what happens? Okay, so I'll stop there. Thank you.
Thank you. Any questions?
Great, tea time.
Is there really time for tea time?
I have a question.
Okay.
I have a
Yes.
question.
Hi.
Hi. Maybe I missed it. Can you tell us a little bit what happens when alpha is 0? What's the major difference between
alpha equals 0 was pretty comprehensively covered by Springer and Hoffer. And in fact, the results for these traveling waves are very similar. So you can do calculations with alpha equals 0, of course, and all of the stable unstable manifold theory goes through, and those constructions work. So it's those three cases, remarkably, despite the difference in their dispersion relations, those three cases are very similar when we're looking at these special waves.
And what's the physical significance of alpha?
Yeah,
there is
so
one?
alpha in the original formulation represents the balance between surface tension and gravity.
Okay,
So
thank you.
I believe it's near a bond number of 1/3.
Okay, thank you.
Any other questions?
So you partially answered this outside of the talk, but when you have sort of these connections of saying, as you said, coming from a maximum down, and follow the two-way numbers like that. So you necessarily don't follow it from a minimum up.
No, you can follow it from the minimum up. The minimum has Floquet exponents -1, near -1.
So here comes my mad science.
Okay.
Is it possible then to have one jump connected to another jump?
Definitely, yeah. I mean, I mean, I showed you a periodic solution with an unstable manifold connected to a periodic solution with a stable manifold, but they both have the other manifolds, right? So this one has an unstable manifold. It could be connected to the stable manifold of this one. Yeah, absolutely, because they still satisfy the jump conditions.
I guess you necessarily just have to check that they have the same speed, otherwise.
No, they will have the same speed. You're just flipping x to -x.
Cool.
Yeah, I'm not sure. Yeah, they might. No, you're right. The speed must be reversed as well. Yeah.
So you just end up with either an
I think. Is that right? There's a symmetry there somewhere. Yeah.
Michael, can I ask
Yeah.
a question?
Hey, Karina.
Yeah, hello. Thank you very much. Very interesting talk. I'm a little bit confused by the scaling transformations at the beginning of your talk, which you used to reduce everything to just 3 cases with alpha equal to 0 and ±1. So are you starting from the equation where you have just one coefficient not equal to 1?
No, I'm starting with a coefficient alpha.
So,
and then you just scale ux and t, and you
yes,
can
yes,
set
understand.
things up.
But what's the coefficient in front of the 5th derivative? Are you assuming that
There is
it's an
no-
arbitrary
you eliminate the coefficient in front of the 5th derivative.
before?
If alpha's equal 0, you don't need to scale. But if alpha's non-zero, then you can scale with powers of alpha. Scale x, t, and u.
Can you show the equation once again, please? Because
of course.
maybe I'm confusing something.
I've got a blackboard here. You want to come down and I'll show you.
I'm in Loughborough, unfortunately.
I know.
Yeah. So, yeah,
there we go.
alpha is in front of the 3rd derivative, right? And you have 1 in front of the 5th derivative. So is this the equation where you start considering scalings?
Sorry, then so let's look at, so alpha equals 0, we don't need to scale. If alpha is non-zero, then I can scale x and u and t and just make
Sure. Yeah, no doubt about that. But my question is that when we kind of deal with these equations in practice, right? The coefficients in front of the 5th derivative is also something. It's not 1, and usually it's actually order epsilon. It's smaller than the coefficient in front of the 3rd derivative. So that means ideally we should be doing the scalings in the equation where we have some arbitrary coefficients in front of all the terms, and then you could have some other cases, I think.
But then you non-dimensionalize. I don't think there's a problem. I mean, as long as you assume.
I think there is a problem because you already use the scalings to bring it to that form. Okay. So to have just 1 alpha with all other coefficients being equal to 1, you must have used the scalings already, I think.
Yeah, I mean, it sounds logical. I'm not sure.
Yeah, okay.
Yeah.
This could be more interesting cases, that's all. Yeah.
Yeah, well, yeah,
Okay.
I don't know.
Yeah, thank you.
Yeah, sure.
Well, isn't it the case that in doing your analysis to get to Kawahara anyway, you're assuming something about the third order derivative anyway, that it's order epsilon, so that everything is in balance anyway.
Well, you want them to be in balance, but yeah, no, I mean, it's right. Should you have alpha and beta in front of U triple X and U fifth order? I think you can just scale.
Yeah, I think just because you've got a U, a T, and an X, right?
Yeah, you've got
you
enough.
reduce it down to a one parameter family anyway.
Right, I'm pretty sure. Yeah, exactly. Yeah, good counting.
I'm thinking of Roman mathematicians. Crazy.
Right, yeah, sorry, don't do numbers.
Any other questions? Remarks? If not, let's thank our speaker
Okay.
again. It's time for tea and we'll resume tomorrow.
Yeah.